Okay, anybody want to volunteer what distinguishes a solid, a liquid, and a gas?
I think it has to do with the molecules, the distance of the molecules, and the speed in which they're moving. A gas, the molecules would be they'll spread around, and a solid, they will all be attached together and hardly move. And liquid, they're attached, but they can move freely within a certain distance.
Okay, what keeps them attached and what makes them move? That's right.
What keeps them attached, I guess, is bonds or chemical bonds, and what makes them move, heat, usually.
Okay, when you
energy.
say chemical bonds, what is a chemical bond?
Ionic bond.
All right, so what force is it that's keeping them together?
Electromagnetic
Okay,
force.
so there's electrical forces, right, between the atoms. Even though an atom is overall neutral, right, it has the same amount of protons as it has electrons, right? The distribution of the charges can make them sometimes attract each other, and sometimes there may be ions they may be missing or have an extra electron, and that gives them an overall charge, and they'll pair up. But usually those kind of bonds, if you have one missing, you'll pair up with something that has one extra. That's only between two. You have a whole bunch of things and they're attracted to each other. It's probably not so much ions, but just electrical forces between things that are overall neutral. Okay? Now, in a liquid, in a solid and a gas, you have two extremes, obviously. In a liquid, you have something in between. And there are certain materials that kind of are like liquid mercury at room temperature, right? It's a metal, but it's liquid. Butter, when it's melting, is that a liquid or is it a solid? Glass, in some definitions, is a liquid. It flows, but it flows very slowly. So there are things that are on the border, but basically, when you understand the molecular theory of materials, that things are composed of little tiny atoms or combinations of atoms into molecules, then those units interact with each other and attract each other to some degree, but there are all kinds of other forces around. And those other forces can make them try to separate. Now, you said something about heat. What is heat?
Energy.
Okay, energy. Now, we'll learn about this today, why, to some degree, why that happens, but you have a vibrational motion of all the atoms, and if they're vibrating, they're banging against each other, and that vibration will, in a sense, tend to break them apart from whatever attractive forces they have. So basically, the more that they're vibrating, the less they'll be attached by those electrical forces. And at some point, they will detach from each other sufficiently so that they can kind of flow over each other. They still stay in one group. Like if you take a liquid like water and you pour it, the water stays together, doesn't just diffuse everywhere, right? And then it hits the table, let's say, and it rolls in puddles and streams and droplets, but a droplet has billions and billions of water molecules. So, and most of it is going like in a stream along the edges and so on. That's still kind of staying together. The pieces are rolling over each other, but they're still staying together. Not like in a solid where the whole thing stays, every piece stays together and where it was. And certainly not like a gas where everything just kind of diffuses and goes up where it wants. Now in a gas, why does that happen? Why does it just spread out all over? The energy of vibration motion is such that it's strong enough to break the bonds. They bang into each other enough, and they just want to move. And if there's nothing stopping them, they'll just continue moving. Now, if you keep it in a box, then they can't get through the holes of the box, right? Depending, of course, what the box is made of. Some gas can diffuse through some materials. So it's trying to get out of the box. If you make a box smaller, can you make the box smaller? If you make the box smaller, what will happen? Gas will become more dense. They make it smaller, become more dense. If you make it smaller and smaller and smaller, eventually what will happen?
They will become liquid.
What?
They will become liquid, the bonds will...
You'll force it into a different state. They'll become so close together, effectively, you might have changed it into a liquid. Okay. Now, it doesn't, the opposite is not exactly the same. If you put in a liquid in a box, you make the box bigger, it's not going to become a gas or something, all right? But when you force, if you force something beyond this, like, tolerance, so to speak, you could change its state. Now, you could change the liquid into a gas by changing other conditions inside the box, like changing the pressure inside the box. There's a lot of pressure in the box, so there's air pressure hitting on it. If you took it into space, it might just diffuse. Okay. If you took a gas,
Wait, I have a question about
Sure.
that. Wouldn't, if you decrease the volume of the box, wouldn't just the temperature increase?
it's exactly what we're going to learn. If you have a gas in some kind of container and you're increasing the volume, and so on. Let's say we wanted to write some kind of formula relating the relevant quantities. Okay, let's say we wanted to figure out what the pressure of the gas is. Okay, and we're going to talk in a minute about what pressure is. We want to talk about the pressure of the gas in the box, or the pressure of the gas against the walls of the box. Okay, obviously, if the box wasn't there, what would happen? The gas would expand to a larger size. If that's happening, that means the gas is pressing against the walls of the box. If it wasn't pressing against the walls of the box, then taking away the walls wouldn't change anything. The fact that if we take away the walls of the box, the gas will expand means obviously the gas is pushing against the walls of the box. Okay, so it's exerting some pressure on it. What should that pressure depend on, do you think? What factors might be relevant? Again, we've gone through this 100 times in different laws. The color of the box, no, all kinds of things. The shape of the box, should the shape of the box be important? We spoke about, let's say, the shape of a block of matter. Does it matter? Is it important in determining the rate of acceleration? Basically, we said only because there's air resistance, right? According to the law of gravity itself, it doesn't matter what the shape is. Does the shape of a molecule affect it? Is it the shape of the box? What are the relevant factors? Something else you mentioned a factor. What factors might be? If we want to write the pressure equals something, what things will determine how much pressure? Okay, the volume, because as we said, if we squeeze it in, we can intuitively feel that the gas molecules are trying to escape and they're banging against the walls even more. If we give it more room, it'll probably exert less pressure. Okay, so we say volume. So let's start with that. We have pressure equals. Again, we're going to start with the simplest possible form of the law and then see if it works. Where should volume go?
In the bottom.
In the bottom, because
the greater the pressure, the greater the volume, the smaller the
greater
pressure.
the volume, the smaller the pressure, smaller the volume, the greater the pressure. Okay. What else might go in here?
The temperature.
Sorry. The force. Okay, force of what? The force of the pressure. Okay. Well, this is the pressure. So, unless you can tell me the difference between what you're saying and the pressure, are you talking about something else?
What
Or?
about force of electrons?
Okay, the force of the electrons themselves
Yeah,
on what?
against the force of pressure.
Okay. When you try to combine the atoms more than a certain amount, all right, they're going to repel each other because the electrons on the outside of the atom are going to push against the electrons on the outside of the other atom. You're going to have electrical repulsion. All right. So you're not going to be able to compress it beyond a certain amount. But that's what you can press it enough so that it overcomes that. And that's the kind of thing that happens, let's say, in black holes and neutron stars, first actually, in black holes and so on. But we're not going to talk about situations where there's such extreme pressure where you're overcoming that. Okay. Okay. What else you said? Temperature. Okay. Where should temperature go in?
Up.
On the top, because
The greater the temperature,
the greater the temperature, the greater the pressure. Why?
Well, I guess I would think of it the other way around, that the greater the pressure.
The greater the pressure, the greater the temperature. Okay, you think of them like heating up as they're. Okay, why? What about this way? Why the greater the temperature, the greater the pressure?
Because they're moving. because the molecules are moving faster. And
Okay, so does everybody think that should be the case, or the opposite, or higher temperature? What is temperature? That's why I said that we're going to be talking about what is temperature, what is heat.
Heat energy. Energy.
Okay, so we have to define, in other words, we still didn't define really what pressure is exactly. We intuitively know what it is. There's a word in English, we're talking about pressure, but we have to be careful because you'd say, oh, the pressure of work this week, or I was in a lot of emotional pressure this week. Obviously, that's not what we're talking about. Okay, there's a very precise meaning to pressure in physics, but we don't know exactly what that is yet. Right? We have an intuitive sense, not only of emotional pressure, but of physical pressure, but we would have to define it more carefully. We also, strangely enough, don't know what temperature is, right? What is temperature? Like you're saying, well, higher temperatures, things are, you have some kind of a sense that maybe it has to do with motion, said about the energy of the molecules or something, or, but it's not exactly clear. Okay, what would you define temperature as? What is temperature?
with respect to motion,
In general.
I would say it would be a measure of the speed at which the molecules are moving,
Okay, why would you say that?
because the faster that they move, the more, I guess that has something to do with the amount of heat that's being generated.
Okay, what is heat?
That would be the energy that's released when the molecules are bumping into each other.
Okay, so how does it release that? What is the energy that it releases? What is that? It releases energy. How does it release energy? What is that energy? In other words, if you say it releases energy, but what does it release? A thing? And that thing is energy, or what is it?
What's the breaking of the bonds? I don't know. I'm just making
Okay,
stuff
It
up.
whatever. In other words, I
heat.
just want to show you that it's not so trivial to think about. We have heat, temperature, motion, energy. They seem to be related in some way, but we have to clearly define what that is. And all of that will be related in some way to pressure also, but we have to define what pressure is more carefully. Okay? Chapter 14, the next chapter, discusses heat. All right, that's why I mentioned that we're going to do a little bit of chapter 14 here, because we have to understand what heat is in order to discuss temperature. Now we have a physiological measure of temperature, or actually a sensation. We feel hot, we feel cold. We can tell the difference between hot and cold, but obviously somebody will say, oh, the room is cold, somebody else will say, no, it's not. Right? You've all been in situations like that. So even cold and hot are very subjective. Probably everybody would agree on whether something is colder or hotter than something else. So we can make qualitative measurements of what is colder or hotter, but not a distinction between cold and hot necessarily. Colder and hotter, yes. Obviously we can take some material, like I mentioned mercury before, and then we know that from experience, maybe you've seen or you've learned, or I'm telling you now, that under certain circumstances, materials will expand or contract. For example, when you heat something up, generally it expands. When you make something cooler, generally it contracts. You've probably seen this in all kinds of different situations. Sometimes even you may have been told that your feet fit in your shoes differently on a cold day and a hot day. On a hot day, your feet expand more than the leather, and it feels more cramped. There's all kinds of, you may have seen wires, strung telephone wires and so on between poles, and they seem more slack when it's hot and more taut otherwise. Tracks on a train way and so on. So there's some context in which we can define temperature by taking some material and seeing how much it expands, and then we can mark off gradation. We can put mercury in a little glass tube and say when it expanded this much, we'll call it such and such a temperature. When it expanded this much, we'll call it that temperature. When it expanded this much, we'll call it that temperature. And then we have a standard, and we can always compare and give it numbers. All right, and we can choose our scales in different ways, what number we put on that. When it changed from yesterday to today, did it change 2 numbers or 5 numbers or half a number? We can decide on our scales, and there are different scales: Fahrenheit, centigrade, Kelvin. You've probably done this in high school. We're not going to spend too much time on it. It's in the book. There are some very simple plug-in problems in converting centigrade to Fahrenheit and so on. Now, so in terms of measuring temperature, we have our own sensation of what's hotter or colder. We can use a property of materials of expansion under heat and contraction in cold to define some numbers according to some scale to make it quantitative. All right, but we still don't know like what it is or why it's happening. Right? Now, we intuitively understand that whatever heat is or whatever temperature is, the more heat you add, certainly the more temperature there'll be. That's what it would seem. Okay? Now, it's not quite so obvious that that's the case. And in chapter 14, we'll see why. For example, it's possible to have water and ice at the same temperature. You take water at 0 degrees centigrade, you have to take away heat from it in order to make it into ice at 0 degrees centigrade. So you're changing its phase. Remember we said before, if you compress it or you do things to it, you'll change the state. Here you have water, which is at 0 degrees centigrade. It still has a lot of energy. It's moving around, rolling over each other. The molecules are rolling over each other. You have to take away some of that energy, some of that heat. And then the temperature stays the same, but because it has less heat now, instead of banging around and moving over each other, rolling over each other as a liquid, it now can't do that anymore, and it sticks together as a solid. So you haven't changed the temperature, you've changed the state. So it's not so simple to say add heat, raise the temperature, take away heat, lower the temperature. But certainly adding heat will change the state or raise the temperature. So, now, can you add coldness to something?
No, you have to take the heat out.
Okay, it's something that people thought at some point that you can add coldness, maybe. But it turns out that coldness is simply a measure of the lack of heat. If you take away heat, then you make it colder. All right, there's no such thing as cold. Just like darkness. Can you add darkness to something? No, you can take away the light. If you take away light, it becomes dark. You can't add darkness. In the same way you can't add coldness. Okay? So we have a little bit of a clearer, maybe, understanding of the connection between heat, temperature, okay, and maybe also about motion. Again, if the molecules are banging into each other very much, then they could be a gas, a little bit less than a liquid, but we want to quantify those things. All right, now, what other factor might come in there? And then we'll get to defining what pressure is.
The number of, well, I remember it from Ken.
Okay, just let's say in terms of, let's say, logic, what? Okay, what other factor? Right, the amount of stuff. Okay, the amount of stuff in the box. If you have the box and you're raising the temperature, intuitively you feel that it'll exert more pressure. And it seems to make sense. The more stuff there is in the box, right, the more pressure it will exert. Okay, the more people in a room, right, the more the wall will get banged by people at the edges. Okay, so we're going to have something here. Where is that going to be? Obviously, on top, the more of that, the more pressure. We're going to have something over here or whatever. Now I'm going to write it as NR, like the number of particles in the gas. That's not really what it stands for. I'll explain afterwards. Okay? And R being like the number of stuff or the amount of stuff. And we'll go into that a little bit more in detail later. Okay. It turns out that this is exactly right. Again, we find an extremely simple, totally intuitive law. Now, the question is this law at the same level of, let's say, F is equal to ma? We had F is equal to ma, which we came up with ourselves after a lot of discussion. Would you say, why would you say this is or this is not as fundamental as F is equal to ma? Which one is more fundamental and why? Or are they the same?
they're the same.
Okay, why are they the same?
Because the acceleration in F equals ma is like saying temperature, because we said that the greater the temperature, the greater the movement of the particles, and the mass is the amount of
Okay, they have similar form, and therefore certain things in here are going to play similar roles. But in terms of the fundamental aspects of nature, let's say, which one, does this or this one, do you think tell you more about more fundamental aspects of nature? Or are they the same? Okay, notice that here we're talking about any mass in the universe. Exert a force on it, the acceleration that will result to be a equal to f over m. Okay, so this relationship holds for any mass, and basically we're talking about, let's say, a point mass, right? Because if we're talking about something big and with a strange weight distribution, we have to know what the torques are, all kinds of things. But for any mass, this will be true. Now, here, in order to define temperature and maybe define pressure, we have to talk about things on the average, like we have gas inside, and we have all kinds of molecules moving, and we're talking about the pressure that the whole thing as a whole exerts on the container. It's kind of average things. There's millions and millions and millions of particles inside this gas, and each of them is reacting according to this law. This law certainly applies to all of them. As a result of all of those particles interacting according to this law, we end up getting, on the average, something like this. And we'll see that a little bit more clearly in a few minutes. Okay, but I just want you to keep that in mind. Okay, the distinction between a law which is fundamental and true for every particle, and something which deals only with statistical properties, something which deals only with large scale, like averaging over many particles. Okay. Now, in order to see, in a way, the connection, let's get a clear idea of what pressure is. What is pressure? What would you relate it to? Let's say something that we may have learned until now. What is pressure? What? Acceleration? Is pressure? What is it? Okay, so what's the distinction between them? Why do we need pressure if we have force?
Well, you can talk about force in terms of one object or one mass moving. But it seems like pressure is the sum of all of, if you're talking about a gas, all of the molecules.
Okay, so it's something average, so to speak. So it's something to do with force and something to do with the force of many things, kind of average. Imagine, let's say you take something like this, okay, and it may or may not, I don't know, if I stretch this paper like this, okay, and I held it and I put this on, it may or may not tear, right? If I made this into a different shape, in any shape, would it be still true? Does the shape matter whether or not it will tear?
Yes.
Why? What shape would tear it, let's say?
If it looks like a fork, is it gonna tear the
If I made it all into a point, if I made this into a sharp point over here, and then I put it on, it's certainly more likely that it'll tear. Why? The force is the same. The weight is the same. Right? I didn't change the mass. So the force that this exerts on the paper is exactly the same. So why does making it into a point make it much more likely that it'll tear?
Because the mass is more concentrated in
It's
one
more
spot.
concentrated. So the force is more concentrated. All right? And that's what we call pressure. All right? A concentrated, what does it mean, a concentrated force? The force per area is greater. Okay? So we take the average amount of force in a particular area and we say, how much force per area? That's what we call pressure. All right? Now,
Say it again, what?
the amount of force
Amount of force?
per area that the force is applied. Okay, like the cross-section area that the force is applied. Now, how do we relate that to our instinctive feelings of pressure? All right, there's another way of looking at it. If you have, let's say, a bunch of atoms in this room, air molecules that are hitting the board, or a bunch of people milling around, running around back and forth, banging into the wall. Obviously, each individual collision happens very quickly. You have a bang, it goes off, a bang, it goes off, a person bumps in, or a molecule bumps in, okay? But what we want to do is take an averaging over many of those. So what we're going to do is look at a particular area and figure out how much force or whatever there was over that area, and that's the pressure. Rather than, because it's not happening uniformly over the whole thing. It's not like this exerts a certain amount of pressure on my hand, on my arm, but clearly it's the same pressure over every little piece of skin over here, because it's uniform. Okay? If it was a strange shape and it was lying on my hand, then maybe it wouldn't be exactly the same pressure everywhere. Okay? Or if it was a bunch of things shot at my skin, I'd feel a little, right? But overall, there might be a certain amount of pressure that I feel as an average. Okay, now what we want to do is compute that so that we'll get a better definition of pressure and temperature. Okay. So we're going to do pressure is defined as force per area, the area over which that force is applied. All right. Now, if we have molecules in a box, how would we compute how much force, or average force, that it exerts on the walls of the box, leading up to the pressure? What's the connection? What can we do? What formula have we learned for force that we can use in this context? Okay, what causes the force? Is a particle coming up to the wall and pushing against it? Not really. What's happening? Okay, right? What's happening in the box? Does a particle come up, stick its hands out, and push against the wall? No. So why is there? What forces are there?
There's the initial force for this, like, I guess, temperature.
Well, okay, that's right. I just want to see that. There's an initial force. What?
Yeah. I think this times temperature.
Okay, but what is exerting the force? You say temperature. Is the temperature is exerting a force? What is the temperature? Is it the temperature is the thing?
No.
I mean, like what thing is exerting the force?
Energy.
Is energy a thing? I mean, what entity is exerting the force? Okay, it's the molecules of the gas exerting the force on the wall. But how would we determine that amount of force, or what have we learned? What's happening? What's happening to the molecule? The molecule's traveling, then what happens? Why is there a force on the wall? It bangs into the wall, and then what happens? Does it stick there? It bounces back. Okay? So what happens when something collides into something else and bounces back? What happens? What happens to this thing? To the thing it collided into? It moves back. Okay? By how much does it move back? Or what relationship have we learned about that?
The force is equal.
We have momentum conservation, and we have a momentum transfer. We have the thing has a certain momentum going this way when it hits the wall. And now what momentum does it have if it's in a perfectly elastic collision? It has exactly the same momentum in the opposite direction. It has exactly the opposite momentum. How much momentum does the wall have now as a result? Okay, or how much momentum was transferred? We had, how much momentum was there? It was mv, going this way. Okay, it bangs into the wall, and now it has minus mv. What's the difference in momentum? How much is the momentum change? Okay, the momentum was mv, and now it's minus mv. What's the change in momentum? P initial equal this, P final equal this, delta P equals P final minus P initial. How much is that?
2 MV.
Okay, so the amount of it is 2 mv. Again, the minus depends on which direction you're looking at. Okay, but the amount of the change in momentum is twice mv. Right? The initial momentum was mv in this way. Okay? The final momentum was mv in that way. How could the total momentum be conserved? It's not the same. One is mv this way, one is mv this way. What has there be in order that the total momentum has to remain the same? There was mv in this direction, now there's mv in that direction. What has to be true in order that the sum total before is equal to the sum total afterwards? Okay, you have mv in this direction, and afterwards you have mv in that direction. They're certainly not the same. What has to be in the system in order for the situation, the momentum before, to be exactly the same as the momentum afterwards?
The second mass must be huge than the first mass, and the second mass must be elastic.
Okay, there's a perfectly elastic collision. It's not that the mass is necessarily elastic. The collision is elastic. Okay. Why? This one has to be huge. Why?
And so that the mass stays same, doesn't move.
Okay, so that this mass doesn't move appreciably. Right, this one has to be much bigger. But in terms of momentum, okay, you have initial momentum is mv in this way. Final momentum is mv that way. The momentum is not the same before and after. But momentum in a perfectly elastic collision, certainly, even not, will be conserved. So how can we say momentum is conserved if the momentum changed? Momentum was this way, now it's that way. Momentum was mv this way, now it's minus mv. So what has to be true
The
in order
wall-
for it to balance the wall?
The wall has to have the equal change momentum,
So how much does it have to have?
2 MV.
It has to have 2 mv in that direction. If the initial mv was this way, now after the collision, this has 2 mv that way, and this takes mv that way. What's the sum of 2 mv that way and mv this way? mv this way. Okay? So initially you have mv this way. That's the total initial momentum because the wall is not moving. After the collision, this has 2 mv that way, and this has mv that way. The sum of 2 mv this way and 1 mv this way is 1 mv that way, which is exactly what it was at the beginning. So the final momentum is exactly equal to the initial momentum, only if the wall carries away 2 mv, the difference between the two of them. All right? So we know that the change in momentum that the wall absorbed was 2 mv, where m is the mass of a molecule, v is the velocity of the molecule. They get it. Okay. Now, how do we relate the force to the change in momentum? What's the relationship? Okay, what's the connection between force and change in momentum? Okay, it's exerting, the molecule is exerting a force on the board, but what we do know is it's causing a change in momentum of the board, right? And yet we're trying to call that a force, right? The only thing it does is collide with the wall, so it transfers momentum. But we're saying it exerts a force on the wall. So how do you get a force out of that? Where does the force come from? It has a transfer of momentum, but we know intuitively you would feel it as a force. So what's the connection between what we know happened in terms of momentum transfer and what we know happened in terms of force? Okay, so remember, we had F equals ma. What's the definition of A? Delta V over delta T, change in velocity for time. M delta V, if the mass doesn't change, we can write it as delta mv over delta T. And mv is P, so this was delta T over delta T. Remember, force was the change in momentum per time, or the change in momentum was equal to the force time for time. We call that the impulse. Impulse equal change in momentum. Okay? So we have this relationship. Remember the relationship? Okay, delta P is equal to F delta T. Remember this whole series of equations. Okay, that's important. Okay, delta P is equal to F delta T. This is equal to F delta T. So what is F equal to? Delta P over delta T. So pressure is force per area, and force is change in momentum per time over area. Okay? Simple step. Now, what is this delta T? What does this mean? What time is that? The time for what? what is that delta t? Time what? The time at which this happens? 3 o'clock in the afternoon? What is? Okay, what does it mean? What is, if f is equal to delta p over delta t, what does delta t mean? Okay, see if you can read this equation. F equals delta p over delta t. What does it mean? How would you read that as a sentence?
It's the time it takes the force to change the pressure.
Okay, something like that, but let's talk about it in terms of what's actually happening. Okay, so make a complete sentence. Okay, so what it is if in a collision during which there is a transfer of momentum over a certain period of time, the ratio between the two is the force. That's one way. Or the force exerted by a particle on another during a collision is equal to the ratio of the change in momentum during that collision and the amount of time during which the collision took place, or any kind of variation. In other words, this is the change in momentum during the collision. This is the amount of time that elapsed during the collision. And the ratio between the amount of change of momentum to the amount of time during which that momentum change occurred, that's what we call force. Okay? So this is a definition of force. Or you can say the amount of force that one object exerts on the other during a collision times the amount of time that the collision takes is equal to the change in momentum. Now, in our case, we have a molecule speeding, banging against the wall. How long does the collision take? It takes a tiny fraction of an instant. Right? What we're going to do, what we're going to look at is some kind of an average, because it's bouncing back and forth, let's say it's in a box. Of course, it collides with other atoms, but let's look at each atom independently as though it's the only atom in the box, and then we'll add more of them, just to make it simple. So we have this atom banging back and forth against the walls, and we're looking at the collisions on this particular wall. All right? So it's banging back and forth. What we're going to do is take some kind of an average. Okay? An average over each particle, over this particle, plus also there's many particles. Right? So then we're going to take an average over all the particles. But we're looking at this one particle. We're going to look at an average, an averaged collision. Not that it goes like this and comes back, but as though during this whole time there was this change of this transfer of momentum. In other words, there was a transfer of momentum of 2 mv to the wall, but not that it happened over that split instant of time, but as though it happened over this whole amount of time on the average. Okay, just to make the calculation simple. Now, how much time elapsed? How would you characterize that amount of time in between each collision? Okay, what can you characterize that amount of time as? What determines that amount of time? Okay, this, that. How much time is that? What does it depend on? What does delta t depend on? What factors?
G, the distance,
The distance that is traveling. Right. What else?
velocity.
The speed that is traveling. Okay, so what is this equal to? Distance equals rate times time. So how much time is this? It's equal to the total distance that it traveled, which is how much? Twice the length of the box. Okay? It's equal to, the time is distance over rate. It's twice the length of the box divided by the speed. Okay? So we're going to put that in here. Delta P over delta T. How much is delta P? It's 2 mv. Divided by delta T. How much is delta T? It's 2L over V. And all that is divided by the area. Okay? Write that down in your notebooks, and then carry it to the next step and tell me how much it is. Okay, now what is A? A is really the cross-section area where that force is. Now the collision itself happened at a tiny microscopic place. But what we're doing is we're taking one atom and it's banging back and forth on the wall like this. All around. Okay, it hits the walls and bounces back, hits this wall, bounces back, like that, roughly. Okay, it's going back, let's say for simplicity, it's just going back and forth. Okay? But it's not necessarily hitting the same place, or maybe it is hitting the same place, but we're taking an average. We're talking about the force on this wall, on this whole wall, as a result of the collisions, or the pressure on this whole wall as a result of this one collision, or average over many collisions. Or what we're going to do is going to take many particles banging all of different places and average over all of that. Okay? So this area is not, just like the time wasn't the time of the actual collision, but was averaged out over the whole cycle. The area is also not the exact specific location of the collision, but the whole wall. So it's averaged over the wall, because there are going to be, again, many collisions per second and many particles. The whole wall is going to experience, on the average, at every point, there's going to be the same amount of collisions or the same amount of force or the same momentum transfer. So we want to try to get an average. So we're going to take this area as the whole area of the wall. It's bouncing back and forth the entire length of the box. The truth is, it's not really, because it's going to bounce into other molecules and come back over here. It's not going to make it all the way here because there's too many molecules. But on the average, it's as though it went the whole way, because some other ones won't make it. On the average, in the simple calculation, it's as though each one is going like this. Okay, if that's the case, what do you get? What is 2mv over 2l over v over a?
L over A.
Okay, the 2's will cancel out.
The V will
The
cancel.
v goes up on top. So you're going to get mv squared. The L and the A are on the bottom. Now what is the L times the A? L is the length of the box. A is the area of the wall of the box. What's L times A? Okay, you have L is the length of the box, and A is the area of the wall of the box. So what is the length times the area of the box, of the wall? It's the volume of the box. Okay, this is the length of the box. This is the area of one wall. So the length times the area is the volume. So you have mv squared over v. Okay? Now this is obviously a very recognizable quantity. Now what did we find here? We have an equation, the pressure exerted by these molecules, right, with the force over the area, is delta P over delta P over A, etc., etc., etc. We found that the pressure is equal to mv squared over v. Okay? This was doing an analysis using basically this level of formula, looking at each particle in a fundamental way, and in the end, we get this. So this is an equation that we can trust, at least in an approximate sense, right? We trust it at the molecular level, so to speak, but in an approximate sense as an average. We averaged a lot to get this. We took the average motion over a whole period, and we assumed that it was kind of going the whole way back and forth, and we averaged it over the whole wall and so on, and we get something like this. This was something that we got before when we thought in terms of quantities that are familiar to us from the macroscopic world, not atoms and molecules, but like pressure and volume and temperature and so on. Now, one thing that we're missing here is, obviously, this is the pressure of what? This is the pressure of the collisions due to one molecule, right? Now, if we're talking about the force per area, the amount of momentum transfer, 2mv, if there are two particles, they'll be twice as much. Right? If there are three particles, it'll be 3 times as much. Obviously, we have to put in here a factor like that nr thing, right? The amount of molecules. All right? So that's going to be in here somewhere, and that's going to be in here. So we're going to have the pressure is the total pressure on the wall is equal to the total amount of molecules that are colliding times the amount of pressure per collision, which is this, mv squared over v.
If we have a two velocity up and down, so which velocity per
Okay,
collision?
we'll do that in a minute. P, pressure, is equal to the number of molecules times mv squared over v. What do we see when we compare these two formulas?
like G equals mv squared.
Basically, at least in this approximate thing, we found a definition of the temperature in terms of the kinetic energy of the molecules. That's very interesting. That's kind of what intuitively some people were groping towards, like that temperature has to do with like energy of the molecules or something like that. You add heat to it, it vibrates more, it bangs in. But with this analysis, we started with one way, like a macroscopic way, defining the pressure in terms of things that are like in the macroscopic world. Temperature, we know temperature, we don't need to deal with atoms, we get temperature. Volume, we know what it is, we don't have to deal with atoms. Pressure, we know intuitively what it is, we don't have to deal with atoms. The only place where we got into the amount of atoms was here. We talked about the amount of stuff, but even that, we didn't really talk in terms of atoms, just the amount of stuff, the amount of gas in the box, obviously is going to be an important factor, even if it wasn't the amount of atoms, but the amount of mass in the box or something like that. So this is all macroscopic quantities, all things that have to do with everyday experience, large size objects. We did a more exact analysis using a more fundamental law, and we came up with this using a lot of averages to build up these small little collisions into an overall macroscopic picture. And we found that there's a correspondence if we define temperature is equal to something to do with the kinetic energy of the molecules. All right? And that's very, very interesting. We came to the same thing from two different directions, and thereby we're able to relate some feature of the world that we call temperature to something very basic, the kinetic energy of molecules. Okay. Now of course, again, there were various approximations in here. One of the things is what you mentioned about the velocity. Actually, the particles are not necessarily going like this, right? So let's say going like that, bouncing off. Okay. So they have some velocity in the x, some velocity in the y, some velocity in the z direction. You have, right, it's a three-dimensional motion. Here, we're talking about, let's say, the component of the velocity in the x direction. All right? How would you relate them? Let's look at, in terms of vectors, if you have a velocity like this, which has an x, a y, and a z component. Okay? What's the relationship between the x, y, z component and the total velocity? If you had, let's take a simpler case of, let's say, two-dimensional motion. It has just an x and a y, okay, without the z. So either in this plane or in this plane, whatever, it's moving like this, it has an x and a y. Obviously, right, let's say it's moving like this, so it'll have a y and an x. Obviously, vx squared plus vy squared is equal to v squared. The total velocity squared is equal to the x component squared of the velocity and the y component squared. So if it's moving like this, it's moving both like this and like that. This squared plus that squared is equal to the total squared. All right, we didn't do three-dimensional motion, but it's the same exact thing. If you have motion in 3 dimensions like that, it's the x squared plus the y squared plus the z squared. That gives you the whole thing. If you go like in the x and then in the y, and then it's hard to obviously do 3 dimensions on the board, like this and like that and like that. This square plus that square will give you this square, and then add this one, it'll give you a 3-dimensional motion. If you picture it in your head, or if you look at the drawings in the book, you'll be able to see them. Okay, so basically, vx squared plus vy squared plus vz squared equals the total v squared. It's just vector addition in 3 dimensions. Now, if the x and the y and the z motion, we'll assume that it's the same, that this molecule has no reason to move more in the x or in the y and the z, particularly since the y, x, y, and z are just defined kind of arbitrarily wherever we want along the axis of the box or whatever, right? The gas doesn't know where we chose it. We're going to assume x, y, and z are the same. So we can, instead of x squared plus y squared plus z squared, we just write 3vx squared. It's the same thing. So Vx squared is equal to 1/3 of v squared. Okay, this Vx squared is 1/3 of the whole v squared. And again, these are all average speeds. All right, so basically what we're going to find is we're going to have a factor of 1/3 in here, or 3. Okay, this is all done in the book, so you don't have to worry about it. All right, when we take into account the different directional motion, we're going to find a 3 in there that comes about because the v square is really equal to Vx squared plus Vy squared plus z squared. Vx, y, and z are all equal to each other, so Vx squared plus Vy squared plus Vz squared is equal to 3 Vx squared, let's say. Okay, so we're going to have a factor of 3 coming. Now, if you want to have kinetic energy in here, and we want to have a half mv squared, so we're going to have to counteract it by putting in a 2. All right, so this 2 times a half will just cancel each other, just to keep this a half mv squared, so it looks like a kinetic energy. And the v squared is actually going to be v squared over 3 for the reason that I spoke of. So you can have a 2/3 in there. Okay, and that's not in the book again, so you don't have to worry right this moment. But that's where that factor 2/3 comes from. And again, we're going to have this nr because this is the momentum, this is the kinetic energy of one particle. If you multiply by the total amount of particles, you have an nr. So that the constant factors will be something like 2/3 nr. That's going to be the constant. But the important part of the equation is that you have kinetic energy divided by the volume. Okay, and that gives us kinetic energy over volume, obviously kinetic energy related to temperature. Okay, so we have a very nice understanding now of what temperature is at the macroscopic scale. We connected between the average kinetic energy and temperature, right? Obviously, if we know what the temperature is, we know how much average kinetic energy. If there are n particles and each one has an average kinetic energy of, let's say, half kT square, or whatever, half mv square, then the total amount of energy in that, the total amount of thermal energy in that gas will be the amount of particles times the average kinetic energy. So that's what we wrote as P is equal to V, okay, this one, P is equal to nRT over V. You can do it in different stages. You can look at first, the volume is proportional to the pressure, right? And then on the bottom of page 393, the volume is proportional to the temperature. Both of those things are clear intuitively. Okay, or on the next page, 394, the pressure is proportional to the temperature. All right, and then you can combine it, as we did on page 395, into the pressure times the volume is proportional to the temperature, or P is equal to T over V, proportional to T over V. Okay, it's the same thing that we did, just in steps. That the average translational kinetic energy, equation 13.8, and I'm reading the bold on the bottom, the average, if you have a bar on top of it, it's a symbol of an average, so the average kinetic energy, which kinetic energy is the translational kinetic energy. Translation means it moves from place to place, of the molecules in a gas is directly proportional to the absolute temperature. Okay, so by that we define temperature. On the next page, it says the square root of v squared with the bar on top is called the root mean square velocity, since we are taking the square root of the mean of the square. Okay, so they have that strange thing on 39. I don't know if you've encountered this in laboratory or something. You have RMS on the bottom as root mean square. All right. Now, why would you have such a strange thing where you take the root of the mean of the square? When you're talking about numbers and you want to take some kind of an average, you may have, let's say, a velocity that has positive amounts and negative amounts. So if you say, let's say there's two atoms, one going in this direction with v, one's going exactly in the same v, but in the opposite direction. What's the average velocity? 0. Okay, because one is going v in this way, one is going v in this way. Together they add up to 0, which obviously doesn't tell you very much about the gas. So you want to find some way of taking the average without losing all that information. Okay, so what you do is you square the velocity, all right, and then take the average. So this square and this square, the negative will cancel out, will become v squared, this will become v squared. But the problem is now you have the average of the square of the velocity. right? So now you have to go back and take the square root of it to get some kind of a normal number. So what you do is you take the square, then you take the mean, the average of the squares, and then you take the square root of that. Okay? So you start with, you have the quantity. You don't want to take the average of this quantity because it's positive and negative, so they cancel each other in the average. So what you do is you square it so that all the quantities are positive. Then you take the average of it. But now you have the average of the squares. It's going to give you too big a number. So to get back within range, you take the square root of that. So it's the root of the mean of the square. Then you take the root of the mean, the average of the square of the quantity. So that would be called VRMS, the root of the mean of the square.
Could you use the absolute value to get the same?
Yeah, right. Use absolute values, and you would have less problem. You would have to square it and take the square root. So the different statistical ways of getting an idea of what the average is, this is one way that's useful in certain circumstances. Temperature is actually what? It's a measure of the average kinetic energy of molecules of a gas. Let's say the temperature of a gas, right, is related directly to the average kinetic energy of the molecules, and we showed that with the equations. So we can define temperature very precisely in terms of quantities that we have familiarity with. What is heat? Okay, so is there such a thing called heat?
Yeah.
It's just a term in English, and we just have to be careful how we define it, how we use it in physics.
No.
Heat basically is a certain kind of energy, right? We see that temperature increases when you add heat, and temperature is kinetic energy of molecules. So obviously heat is a form of energy. If you add heat and you're raising the temperature, that means that you're raising the kinetic energy. So obviously heat is a form of energy. So it's just a word to describe a transfer of energy, basically. When you're transferring energy from one object to the other through changes in temperature or changes in state. Like, remember we said that it can stay at the same temperature, change from water to ice or water to steam, and you're obviously adding heat, but you're not necessarily changing the temperature. So heat is, when you're transferring energy from one thing to the other, in certain contexts, it's called heat. But the actual energy is the kinetic energy of the molecules. The average kinetic energy of the molecules gives you a measure that's called the temperature. Now, obviously, if you have a whole big piece of metal, and the same metal but a smaller amount, there's much more kinetic energy of molecules in the bigger one than there is in the smaller one. Each molecule might have the same average kinetic energy, but there's simply more molecules and therefore more total energy. So obviously, the internal energy of this piece of metal as a total is much bigger than the internal energy of the smaller piece of metal. The average internal energy is the same. It's just there's more of it here, so there's more energy. So the temperatures of the two are the same because the average amount of energy of the molecules are the same. That's the same materials at the same temperature. But the amount of heat that the big one contains is obviously more than the amount of heat that the small one contains, or the amount of heat that you would need to bring the big one up to a certain temperature is much more than the amount of heat that you would need to add to the small one to bring it to the same temperature, right? Even though the average is the same for all of them, simply in terms of the amount of molecules that there are. So there's three different words that you should know the difference between them. One is heat, one is thermal or internal energy, and one is temperature. Temperature is a measure of the average kinetic energy of the molecules in the gas. Heat is when you're transferring the energy from one thing to the other, you call it a heat transfer. But actually what you're transferring is basically kinetic energy, so the molecules will vibrate more. We feel air molecules colliding against our skin, all right? On the average, there's a certain amount of molecules that bang into our skin over a certain area, etc. Instead of a gas banging against the wall, we have air banging against our skin. It's transferring momentum, etc. And it's the kinetic energy of those things that determines what we call the temperature. Our body is constructed in such a way that it converts the kinetic energy of those gas molecules, the air molecules. They're vibrating, and they have a certain amount of kinetic energy, and our nerve endings convert that into a sensation of what we call cold and hot. Cold and hot are not physical quantities. They're our sensation of corresponding to physical quantities. You have motion, bangs into our skin, causes firing of nerve cells into our brain. Strange things happen in there. It goes into our consciousness, and we feel a sensation of cold or hot. Okay, but not that the molecule is cold or hot. The molecule is vibrating. That's all. It's vibrating more or it's vibrating less. It's neither cold nor hot. But we call it cold or hot. Now, the one thing I just glossed over was this NR. Okay, and I said it's the number. It's not, I said it's not really NR being the number. It's something else. If you're talking about collisions of molecules with a wall, and what we're concerned about is the total amount of collisions happening, because each collision transfers a certain amount of momentum. We want to know how much stuff there is in the box, how many atoms or whatever are colliding with the wall. Now, to some degree, the mass of each atom is important. Okay, because it's moving with a certain velocity, it has a certain momentum, that's the mv square over there. Okay? But when we want to figure out how many collisions there are, what we want to know is basically how many atoms there are in the box, or how many atoms there are per square area colliding, the wall of the box. Right? Now, let's say I'm given the total amount of mass that's colliding. So that'll help me figure out the momentum transfer. But if I want to do it in terms of each individual atom has an mv square, and then multiply by the total amount of atoms, how would I find the total amount of atoms given the mass of the atoms altogether, given the mass of the gas hitting the wall? So let's say there's a gas, let's say 1 gram of gas striking the wall at any given instant. Okay, how many molecules are striking the wall? Obviously, it depends on how many grams per molecule. Right? If I have 1 gram of stuff hitting the wall, and I want to know how many molecules there are, then obviously it depends on how many grams there are in each molecule. All right? So sometimes what I'm interested in is the mass of a molecule. Sometimes I'm interested in how many molecules there are, right? And I could be interested also, let's say, in the volume of a molecule, right? In different certain circumstances, you'll be interested in different characteristics of the molecule. Now, the volume of, let's say, an atom depends on how many electrons there are in the outer orbit and so on, but not to such a tremendous, fantastic degree. It's not so relevant because the amount of space that the electrons take up is very small. I don't know if you do this, let's say, in chemistry. It's like the sun with the planets around it, all right? Most of the volume of the solar system is emptiness, right? You have a sun, and you have empty space, and then you have a planet here. All this volume is empty except for this planet. And then you have another planet out here. All that volume is empty except for the planet. Most of the space of the solar system, the tremendous vast proportion of it is emptiness. If you took, let's say, the solar system is like this, and you took that whole, let's say, volume, right, or area, okay, of the solar system, and you took all the planets and the sun and put them together in one place, right, the great vast majority of this would be empty. Okay, it's just mostly empty. The same thing in an atom, roughly speaking. Again, you can apply these models, the macroscopic type of reasoning, to the microscopic world. The electrons and the protons don't exactly have a particular place, aren't located in a particular place, and that's something that you would learn in quantum physics. But if you consider it that they take up only a certain space and they have a certain shape and size and so on, if you took them all together and put them, scrunch them up together, it would take up a tiny amount of the volume of the atom. Okay, most of the atom, you have electrons zipping around, so to speak, in a nucleus. If you took all of that stuff and put it together, it would be just a little bit bigger than a nucleus. And most is emptiness. And then you have intermolecular spaces or interatomic spaces. The two atoms are not touching each other. They're, even when they're very, very close, like in a solid, there's still some distance between them. Okay? So we're not usually concerned so much with the size of the atom. What we're looking at is some kind of average, taking the total mass of the atom distributed over the whole size of the atom, or the total mass of all the atoms distributed over the size of the container that all these atoms are in. If we're looking for the amount of atoms, how do we figure that? We'll take the total mass of the substance, and we have to take into account how much mass there is in each atom. An atom which has 12 protons and 12 electrons, 12 neutrons, let's say, will obviously have twice as much mass as one that has 6 protons and neutrons and electrons. All right, so we won't know the amount of atoms just by knowing the total amount of mass of the substance. Right? If you have 1 kilogram of substance and a kilogram here of another substance, they don't have the same amount of atoms in both. This one has a kilogram because, let's say, each atom weighs a gram. It's a ridiculous amount just to make up, right? It has a kilogram of substance. Each atom weighs a gram, has a gram of mass, so there's 1,000 atoms. This one, each one, let's say, is 10 grams, so there's only 100 atoms. Each atom is 10 grams. Okay, so you need to know how much mass there is in each atom to be able to figure out how many atoms there are altogether given a certain amount of mass. This number R, this number N, okay, takes into account that. You figure out how many atoms there are in a given amount of mass, right? And obviously it depends on the atomic mass. The more the amount of mass in an atom, the fewer amount of molecules or of atoms you need to make up a given amount of mass. Now, did you all encounter the word mole in chemistry? You must have assumed you've taken it, right? So you know what moles are. So N is just the amount of moles, okay, which is exactly what I've been saying all this time, but basically you care about the amount of atoms rather than the exact mass. Then you multiply by the kinetic energy, which takes into account the mass of each